I'm Robinson. I work at Petrobras. It's a large oil and gas company, and we invest in technology through cooperation agreements and partnerships. And I hope my slides will come up soon enough. But yep, I'm going to be showing you guys a little bit of some of our partnerships that we made and tell you what we're looking for in the future so that maybe we can keep chatting after this talk today. For those of you who don't know, Petrobras is an oil and gas company, owns a whole bunch of vessels, production vessels, and invests a lot in R&D every year. This is an image of a vessel that we own. When we started talking about machine learning back at Petrobras, we did some experiments with semantic segmentation. The results were great, but now we came with the question, how are we going to scale this? How are we going to serve this to people? How are we going to use this in our business process? So we developed with a partner Street View-like solution, and it allows us to do 3D measurements, navigation, and only requires a very simple hardware. So this is an example of a partnership that we make to solve problems that we have. And it's a success. We have more than 4,000 users, and we expect to reduce 18,000 man-hours per year on offshore platforms. And a huge image collection. And this solution today is being popularized, is scaled a lot, is being used all over Petrobras right now. And naturally, with those 420,000 images, we started looking at, again, semantic segmentation to explore object detection and find ways to map problems on offshore platforms on a scalable way. So we have a partnership that's working on that problem right now. But we have a lot of data in databases. So we needed a solution to search and find information. So we went in agreements and developed a solution to help us find, analyze, and visualize data. It's been very helpful and add a lot of value because it comes with a knowledge graph that's being used as a resource to start different projects and developments. It's been very helpful for us. It allows us to standardize knowledge. Now, finally, a third investment that we made over these past years, it's an integrated visualization tool that helps us to see problems in 3D space, help us manage services offshore, the installations. So we're working on an ecosystem of tools. Each tool is a partnership. It could be a startup. It could be an agreement. And I'm going to show you guys a few of the things that we are working on with research labs right now. We hire research labs. We're exploring human in the loop to use all the data we have been collecting on Street View. We want to improve efficiency of the object detection interacting with the user. But not only that, we want to be able to have a solution that helps us to recommend information to our users so that they can find information they need whenever they are navigating the solutions. So these are all cooperation agreements that we entered over the past couple of months, actually. And finally, Kronos, it's a tool to do multi-objective optimization. It helps us to minimize resources that are required to do maintenance on the offshore installations, right? So what we want to achieve is get all these pieces and see the concept of a platform. We expect to find a partner to work on that platform for us and help us reduce the distance between the user and the people who we invest on to develop solutions for us. So we want to reduce the time to market, research time to market. We want modularity, and we're looking for very specialized startups. So we're looking for strong research labs as well. Right now, we're looking for a data hub solution. We started already. We're looking for model management and always talking about specialized plugins, startups that could solve very specific problems that we have. And we have a whole bunch of open challenges to solve and a large investment base to explore with startups on our way to solve these open challenges. So some final words. We want to invest in highly technical stuff, be unique, it's important for us, and you can be part of our journey. Just reach out, and I'll be here after the talk for a couple of hours before I fly back home. Okay, so that's it, everyone. Thank you. That's my contacts. Hopefully, you enjoy.
All right. Hi, everyone. Hopefully you can hear me. So that's quite a nice, lengthy intro. I really got to remember to trim that down. Yeah, we're going to talk today about an ongoing research program at the University of Toronto, trying to bring autonomous driving to Canada. We all know it's going to be a battle because we have these horrible driving conditions that affect us all the time. There's a lot of ongoing efforts that are piling into this research. First off, I want to highlight the Toronto team. This is now, we've 5-peated, so we're in an auto drive competition run by GM and SAE, and the last 5 years in a row, we've come out number 1. There's 100 students every year building self-driving car vehicles from scratch using a GM Bolt, strapping on their own sensors, doing all of their own coding. Really an exciting effort, and a lot of great engineers getting amazing training in the autonomous driving industry out of that effort. As I mentioned, we have now 250,000, I got to update the numbers, people that have been through or have at least downloaded or watched one video on my Coursera self-driving specialization. I did this together with John Kelly. It's been a really, really exciting ride. And we've done a lot of work collecting data sets specific to the Canadian environment. So the Canadian Adverse Driving Condition data set, which I'll talk about, and Boreas as well, which was done by a colleague, that are really trying to highlight what it means to come to Canada. Those of you that were listening to the news over the weekend, we heard about Tesla's self-driving program now being launched in downtown. And one of the big worries I have, of course, is how it's going to behave when you've got thousands of pedestrians, hundreds of vehicles, and snow everywhere. It's going to be a giant mess, I'm pretty sure. But we'll see soon enough. Somebody's always uploading YouTube videos to tell us how bad it works. So that's always insightful and exciting. Okay. Oh, here we go. So just a quick set of highlights. I work specifically on 3D object detection quite a bit. This is really the challenge of converting LiDAR and or camera data into 3D locations and bounding boxes for objects. And our first big hit was the AVOD, the aggregate view object detector, which showed that you could do these things fast enough to run them real time. And so we built and designed this network. It was top of the CADC benchmark, for those of you that know what that is. It's a self-driving car benchmark back in 2018. And we used that software directly on our own self-driving car and ran around Waterloo on public roads, detecting vehicles at about 50 to 80 meters quite reliably. Since then, we've worked on probabilistic representations within the deep learning models to improve feature propagation from vision to the 3D world. And so here we built a BEV-based network called CADN, which uses a depth distribution to better capture the uncertainty associated with where objects are when you project them from the 2D image into the 3D bird's eye view. And this led to significant improvements on the benchmarks and was really a nice step forward in terms of monocular 3D object detection. And then our most recent work, let's see if this works. There we go. Our most recent work was dense voxel fusion. This showed a really reliable way to extract maximum information from both camera and LiDAR simultaneously. There was a bit of a surge in the literature in using camera first, followed by LiDAR in order to do 3D object detection. And we showed that that wasn't necessary, that you could use them simultaneously and extract maximum density features in a dense voxel fusion approach. And again, we hit the top of the benchmark, so we're very excited about this stuff. So this is our most recent work coming out. Okay, but today we're going to talk about the bad weather, and we all know what this is like. We know driving in Toronto in winter is a mess, right? The situations can change really quickly. The visibility isn't always great. Other drivers can give us a lot of grief, a lot of problems. And everybody's sort of changing their behavior and constantly adapting to the conditions that happen. It's not a steady state. It's not easily trainable for ML. It's a harder problem and a bigger problem than sort of typical driving. We also know that this is one of the worst situations for humans as well. There's a significant increase in incidents, accidents, and delays when you're trying to drive in this kind of adverse weather. And just crazy, crazy stuff happens. This was a snowstorm in January of last year. I think we had about a foot of snow. Wasn't it 60 centimeters, if you remember that horrible day? The 401 was completely clogged. These trucks are absolutely stuck. If we let this video play long long enough, this poor tow truck is trying to tow an actual transport out of the snow, and it just never works. And then you've got all kinds of new behaviors that appear, vehicles that you only see 4 or 5 days a year, doing things that have to be done but that maybe don't exist within your data set. It ends up being a really tough challenge to try to capture all of the things that you need to be able to handle as an autonomous vehicle, right? We refer to this essentially as the long tail problem. There's so many things out there that we don't see very often that we still have to understand and behave correctly for. So I kind of categorize all the problems with adverse weather as follows. We have the physical scene variation, so the actual world looks different. We have a slow-moving slide. There we go. All right. We have sensor data corruption. So the actual collection of images and of LiDAR is different. And I'll talk a little bit more about that as we go along. We have wildly different behaviors, people pushing cars, cars sliding sideways, not stopping at stop signs, all these kind of behaviors that we don't normally have to handle. And we have a lot of new planning constraints. The road lane markings don't necessarily align with where people are driving, right? We all know this. We follow the tracks of the car in front of us, and that may be right in the middle of 2 lanes in a normal map that the vehicles would have. And then finally, in a split second, your traction can change, right? And so you need to have this ability to either predict, to be told about, or to infer what kind of driving condition you have at each one of your 4 wheels in real time in order to survive as an autonomous vehicle. So as mentioned before, I think one of the big pieces that academics are able to do is to release and make publicly available open source data sets that allow researchers to really understand the complexities of these problems. And so we spent a long time while I was at the University of Waterloo collecting winter-specific driving data sets, and we released those as the Canadian Adverse Driving Condition Data Set, or CADC. It's got a fairly standard, although now maybe a little bit under-dense representation of sensors. We had 8 cameras, and all 8 omnidirectional. We have just a 32-beam LiDAR, so it's a fairly sparse LiDAR. But then we had high-quality Novatel GPS, INS, vehicle control data, camera, IMU, et cetera. We collected on the order of hundreds of hours of driving and then pruned it down to the craziest set of winter conditions we could find. And we did try to mix up, so we have some clear weather, we have some moderate snow, and then we have some really difficult and nasty driving conditions, all collected in about 7,000 frames of annotated or labeled data. This covers 281,000 cars, et cetera, 60,000 pedestrians, and only 700 bicycles. Not surprising, there's not a lot of bikes out there in the snow in winter. So just to give you a sense for what the conditions look like, this is a typical arterial in Waterloo, right? Lots of open space, easily identifiable vehicles. This is a relatively benign challenge for our existing object detectors and tracking systems. As you increase the weather conditions, you can see the road surfaces change, you can see the vehicle appearance changes, although their geometry is still fairly similar, right? So all of these things affect the way you can do the detections, and you can see here our monocular camera system is still managing quite reliably. And then finally, you can see situations where there's an immense amount of splatter collecting on the lenses of the cameras. We have really nice sequences where we have, the evolution of degradation of the visibility for these cameras over 10 minutes, right? Because we didn't have wipers and we didn't have blowers and we didn't have heaters all cleaning these lenses constantly. So you can really get a full spectrum of how bad it could potentially be. This kind of situation can easily arise even if you have a fully equipped self-driving vehicle, in that you're gonna have some car drive through a large puddle of slush, and that'll get sprayed up onto your vehicle, and it'll be seconds before it's cleared, right? So we do need to be able to handle these situations, even if we have all the mechanical advantages of a well-designed self-driving car. Okay. Oops. So just finally, let's see if I can get this going. The clicker is awesome. On the LiDAR side, I think this is a nice little representation. So what we learned quite quickly was that LiDAR has a lot of issues with precipitation, right? If those snowflakes get large enough, they can reflect a significant amount of the light that's being output by the sensor, and that leads to a lot of backscatter. But that backscatter tends to be within 10 to 12 meters for this particular sensor of the vehicle itself. And that turns out to not be that difficult a situation because everything outside of that is still readily visible. And that means that you can still do regular object detection outside of this sort of donut of confusion. The other thing that we really noticed, which you can see here, is that when there's a solid object in the background, there's less backscatter visible by the LiDAR. And what happens is, this is a sensor-specific characteristic. The LiDAR are always picking the highest peak they get in return. So if you're taking a long-range view down a roadway where there's nothing returning a strong peak, you're more likely to get backscatter than when you're looking at a building. And so these kind of characteristics are really important to understand and to learn, and we can actually simulate these quite well, and then therefore use clear weather data sets to, I guess, snowify them and actually teach our networks to be invariant to weather conditions such as snow. So the more we understand about how LiDAR and camera behave in these adverse weather conditions, the more we can replicate that and eliminate it from the concerns that we have for our object detection. Awesome. Let's try again. Okay, and so we did a bunch of benchmarking where we showed that we were definitely providing a difficult data set here. So we used some existing detectors like point pillars and PVR-CNN. We also threw in our monocular 3D object detector known as CADC. And what you can see essentially is, relative to sort of standard benchmarks such as KIDI or Waymo, we've got a significant drop in the average precision at an IOU of 0.7. For those of you that know what I mean, awesome. For those of you that don't, it means essentially that this data is a chunk harder than what we've seen in other data sets, and the existing methods need to have some ability to adapt or modify the way they identify objects when snow is present in the scene. So just a bit of a summary here. Awesome. So one of the first things we did in terms of addressing those issues specifically with LiDAR was to see if we could just clean up the point clouds, right? Can we remove all of the artifacts that are confusing and simply recover the situation that exists as if the snow wasn't there? And so what we tried to do was build a filter or just an automatic removal of the snow noise in the point clouds. And this, using the existing techniques, led to a significant removal of all of the cool features that were at distance, right, where the LiDAR data necessarily gets a little bit more sparse. And so you can see here on the left, we have the raw point cloud. In the middle, we have the standard state-of-the-art at the time radius outlier removal filter, which essentially just clears things out based on a search radius. If there aren't enough neighboring points, that point gets classified as noise. And what we did was essentially adapted with knowledge of the sensor itself on the expected concentration of points in a clear weather scene. And we could use essentially a dynamic filter that adapts to the local environment and retains features or LiDAR points where there are still features out at a further range. And so this worked really well. And we were able to capture significant improvements in terms of localization and mapping. So I'll just show a bit of the results here. Let's see if this is playing. Awesome. Okay. So here we capture on the top. You can see in the top left, you can see the raw LiDAR point clouds and exactly what we were describing before. You can see that clear backscatter around the vehicle. When we do the filtering with our dynamic radius outlier removal, you can see we retain all of the interesting features in the environment for localization and mapping, and we have a nice cleaned up point cloud essentially, right? So we're able to then go ahead and construct maps using this data. We're able to do localization on the fly, and all of that is essentially unaffected by the fact that there's snowfall causing negative effects on the LiDAR data as we're moving through the scene. So very happy to see this. This was actually the LiDAR localization approach we used on our autonomous self-driving program. And this is what part of the route that we drove autonomously on public roads in Waterloo back in 2018. Awesome. So we're able to show that we were significantly more capable at identifying snow. I had a set of students who still hate me to this day because I made them individually label the points in the LiDAR point cloud for about 2 weeks. I think they went through 15 or 20 point cloud samples and individually labeled the points as snow or not snow using their best judgment. It was a lot of fun for me. And we were able to show that we got a very large percentage of those points automatically labeled by the DROR filter as a function of after we applied it to the system. Similarly, when we use some of the other methods, we could see that essentially they eliminate all points. So in the top on the right, you can see the competitive method essentially eliminating all points beyond 20 meters, right? It was unaware of how LiDAR density changes as a function of distance, and therefore just over-filters and removes all the interesting features in the scene that are essential for localization, whereas our method worked quite reliably. So really proud of this one, and it's starting to pick up steam. People use this now as a nice, human-driven baseline with which to compare their deep learning methods to do the same thing. So you can imagine, obviously, whenever you see this kind of pattern identification kind of problem, there's an ML solution that's willing to take on whatever human engineers can come up with. But this is a really strong and super efficient baseline that we can run on all of our LiDAR data. Awesome. Okay. Oh, cool. All right. So the next thing I wanted to talk about is a new project that's coming out where the idea was that we would like to improve the performance of our adverse weather-based object detection by using self-supervised learning. So this is an emerging technique where we don't immediately focus on labeled data, but we start by providing just copious amounts of unlabeled data from which we want to extract features for what's known as a pretext task. So this is a task that you apply that's close to what you'd like to do at the end, right? Some sort of downstream task that's your real objective. But given that you don't have labels, you try to come up with a pretext task that you can automatically generate labels for, and then learn how to process all of these large data sets first, giving you beautiful features in advance that then translate into better performance in the downstream task. So what we came up with for the winter autonomy was a way of trying to create both real and simulated weather, and then try to force our network to provide features that were similar for both of the tasks. So what we do is we find a ground plane, we remove the ground plane, we cluster every object in the scene, and we try to express that cluster with a set of features, and we try to match that feature cluster representation to similar feature clusters in either snowy data or unsnowy data. So we're always comparing clear data to snowy data, and we're doing this either by simulating snow in the LiDAR point cloud so that we can basically make a clear weather data set snowy, or by taking a snowy weather data set and removing all the snow, right? And therefore make a snowy weather data set clear. And so by doing this, by having both directions, we're trying to avoid any kind of overfitting to a particular simulator, and trying to take advantage of all of the different data sets that are available to us. And so essentially we do this in our two sets of pipes, and at the end, the task that we're trying to get the networks to agree on, right, are ones that extract similar clusters with similar feature representations, regardless of whether or not there is snow, be it real or artificial, in the data that we provided, right? So we already know how to remove filters, remove snow. We did this by filtering with our DROR filter. And so once again here you can see now the LiDAR point cloud. This is snowy data collected for which we can extract a ground plane, and then you can see the individual clusters above and below being reasonably similar for the two different sets. Similarly for the, there we go. Similarly, for the snowfall simulation, what we did was we relied on some work by Honor from 2022, where they actually, for every LiDAR point cloud, simulate snowfall precipitation as circular orbs of varying radii, which then either absorb LiDAR points scans or scatter them back to the sensor. And so we end up with that same sort of backscatter pattern. And again, what they did was they fully replicate the entire spectrum of energy returning to the sensor, and therefore we get that same artifact where when you don't have a strong object in the scene, you get much more backscatter than when you do, right? So all of those things are visible. Similarly, we had a wet ground simulator that we could add, which does a lot of absorption, and so we end up with fairly representative LiDAR point clouds. So here again, you can see kind of the clear weather data on the top, and you can see the snowfall generated from simulation on the bottom. So this is another representation of how we can add snow, and we can now have these pairs of data that we can match and learn from in a self-supervised manner. So we're still at the preliminary stage with this. We've got some interesting results. When we do this on fog, we find that our simulators are highly representative and the data is significantly more difficult. And so we see a significant advantage for fine-tuning with weather augmentations. But when we do this on snow, we see that training from scratch is still most effective. These are still small data sets, and we need to really scale this up in order to get the real advantage of SSL. And we also need to push into the weather extremes. So if you have light snow, it's really, as we sort of can see from those lighter point clouds, it's not actually as difficult as it might seem in order to do 3D object detection on those scenes. But definitely, if we want to cover the full spectrum of conditions, we're going to see advantage from this kind of approach. So we're excited to push this forward going on with the project. Lovely. Okay, I'm having fun up here. And this brings me to sort of my closing topic. So those are just 3 little vignettes of some of the work going on in my lab in the winter autonomous driving. And what's happened is we've now, after 2 years of waiting, finally been awarded a major research program at the University of Toronto. It's an ORF-RE. For those of you that are in academia, you'll know what that means. And it has about $9 million of funding over 5 years, which is going to allow us to grow our team to about 30 students, faculty, and postdocs, and a program manager, and really sort of put a spotlight on this difficult challenge. So we're really excited to kick this off, and we're going to hopefully see a lot of exciting results in the near future. This wouldn't have been possible without our great partners. So we're working with GM Canada, who are really going to provide a significant amount of resources in terms of test facilities, engineering time. They've similarly got a lot of effort going on here in Oshawa in terms of AV testing and development. So we're really excited to work with them. We're also working with LG, Applanix, and Algolux. So Applanix, obviously, on the localization and mapping side, and Algolux, those of you that maybe have not heard of them yet, they're a really exciting company trying to develop all-weather autonomous perception modules for OEMs, so that's a perfect fit, and they're supported significantly by GM, so it's a natural combination for us. So we're really happy to have these great partners and look forward to working with them in the future. I think I've already said all that. This is just a cool picture of our garage. I just couldn't delete this slide. What can you do? And so once again, we've got these 5 different challenges, right? The physical scene changes, the sensor data is corrupted, people do crazy things, and cars behave in wild ways. We have difficulty finding the roadway, and our traction changes at a moment's notice. And conveniently, I have 5 researchers that are spearheading each of these initiatives. So I'll be in charge of object detection and tracking. Professor Tim Barfoot is a well-renowned researcher in localization and mapping, and he'll take on that challenge. Igor Gilichinsky has joined the University of Toronto just 2 years ago, and he's done a lot of really interesting work in behavior and prediction for autonomous vehicles. And of course, John Kelly and Angela Schulich have been my longtime colleagues at UTIUS now, and they'll take on planning and safety-critical learning for control. Angela has recently moved to TUM in Germany, but she's going to continue to be a part of this project and still has a significant presence at the University of Toronto. Okay, so with all that, I think I've taken up a reasonable amount of time, so I'll close it there and leave you open to any questions. So thanks for listening. Yes.
Thanks for the talk. My question is, would we run into similar issues in this type of weather or rainstorms, where you're introducing particles, and for that, the data set might be smaller, so it might be more challenging to figure out how to solve it?
So precipitation of any kind changes the sensor characteristics, absolutely, yes. And so what we're doing, right, is essentially trying to identify that region that's kind of worst case, right, where we know all kinds of aspects of autonomous driving change. But in a more subtle sense, when it starts to rain, roads get a little bit more slippery, right? There's rain droplets on your lenses, so you know the sensors are going to have difficulty seeing everything clearly. And so, yeah, you still need to be able to adapt to those. What I find is that it becomes a real spectrum of difficulty, right? So most of the data we've worked on as researchers has been in clear weather, right? The kitty data set is notoriously sunny and green, right? Waymo started to introduce a little bit of rain, but it's only a small portion of the overall data. And so you have this challenge that's kind of sitting there in the background, and it's not clear exactly how hard it's going to be, right? Particularly for perception, obviously, is the way I think about it. On the planning and control side, it's definitely a whole new beast, right? The behaviors needed to survive are often kind of problem-solving behaviors, right? So you enter a downward slope and your vehicle starts to slip. This is not something that has part of any simulator to date, from what I've seen. And we need to have vehicles and AI capabilities that can, reason on the fly that things aren't working, or can somehow be trained against the whole spectrum of possible traction situations. Yeah. So I think there's a lot to do in this area. Yep.
Thank you.
There we go.
Hi. First off, thanks for the talk. That was fantastic.
Oh, great.
I was intrigued and surprised to see so much on LiDAR, especially in simulation as well. It's really interesting. And I'm curious to know what you might say to other AI leaders like Andrej Karpathy, who have abandoned LiDAR and are trying to approach the situation fully using vision.
So there's only one I know of, and that's Tesla, right? That have claimed that they can do this whole problem without vision. I come from an engineering background. I think of redundancy as essential to safety. Yes, it's technically possible. Humans have proven that we can drive cars with only vision. Well, vision and audio, right? And feel. So there's no direct requirement for LiDAR, but it's an incredibly informative sensor, right? To get a full 3D model or representation, a sampling of the entire space around the vehicle is immensely valuable for precision maneuvering, for prediction. None of the things that we do as humans are nearly as easy for AI systems, right? The full world model that we carry around, that we've been developing since birth, that teaches us everything about physics and lighting, and right, these are all, they exist in the data sets, but that's not what our networks are learning. Our networks are learning pattern recognition on a finite set of samples, and we somehow generalize that knowledge, right? And we internalize it and distill it into things that can apply to new situations. And that to me is like the big open question. That's the hard part, right? In terms of how we get to this kind of autonomy that can handle these situations it hasn't seen before. And so, throwing out LiDAR, throwing out radar, this is, in my mind, a recipe for disaster, right? That vehicle will be blind the second there's spray on those lenses, right? It's totally fine for the full self-driving beta program, where the human driver is constantly vigilant and, in fact, forced to pay attention by, adding sort of disturbances and crazy maneuvers into the way the vehicle behaves to make sure they're always paying attention, right? But it's a huge gap between having a driver that's always paying attention and then suddenly having a driver that never has to pay attention. This is a really difficult jump. It's a really difficult leap to make, right? There's a lot of history where test programs have failed because the cars were getting too good. So, the humans only needed once a month or once every 6 months to actually make an intervention, or, in another way of saying it, once every 10,000 or 20,000 or 50,000 kilometers, right? As that happens, it becomes impossible for humans to monitor, where nothing is required of you for hundreds of hours, and then suddenly your life is at risk in 4 seconds, go, right? It's an impossible task. And so in my mind, having these redundancies, having this sensor system that can see everything independent of, right, any kind of failure on the vision, it's going to be really important to actually prove that we can do this safely. And radar is another example. Yep.
Yeah, I think we only have time for one question.
Any other questions?
Yeah, I'm here.
Oh, there you are. Yep.
Thank you for the talk. That was amazing.
Cool.
I have 2 questions. One is just a follow-up from the question that was just asked regarding a LiDAR. Is there a special case for LiDAR in such kind of weather conditions when it's not sunny and perfect? which makes LiDAR more important in, for example, rainy and snowy conditions? And has this data informed you about that in any way, because of which there was so much focus on LiDAR? So that is question number one.
Yep.
And question number
Let's
two.
pause there, and then you can ask the next one. That's great. So are LiDAR sensor manufacturers trying to improve their sensors to avoid issues with? Absolutely, yes. You can already get not only the first response and the highest response, but also the last response from the LiDAR beams. And that's a really interesting thing. You'll see it in the Waymo data set if you ever play with this. You can add in the final response as well, and that actually just densifies the point cloud. And so you see things that reflected off of windshields, that went through bushes, and you can actually better reconstruct the ground plane and objects in the further distance based on those final echoes, those last echoes. It can also be noisy, and you get a bunch of scatter that's under the ground and above, right? So there can be multipath issues and things like this that affect that. So it's a difficult challenge for the sensor manufacturers. I think what we're trying to do is make the networks robust to those kind of disturbances, but you're absolutely right. The way that the sensor data is going to change over time is going to be important to us, right? So we do need representative data in order to ensure that the simulations we develop capture the effects that we're going to see in the real live point clouds. Yep.
Got it. Thank you. And my second question is regarding more philosophical in nature in terms of autonomous driving. How much of the autonomous driving problem do you think we can solve using just AI and vision and LiDAR data as opposed to inter-vehicle communication? For example, the roundabout problem is an interesting one, right? Humans almost have this hive mindset of understanding like the dance between when to enter a roundabout and then when to exit.
Yep.
How much of that can be solved by pure autonomous driving?
I think we can solve it all. The inter-vehicle communication is going to be a beautiful additional layer of information that's going to make self-driving easier. But if we can't internalize all of the decision making and all of the source data collection into the vehicle, right, we're always going to be dependent on that communication channel, which can be disrupted, which can be delayed. And so in my mind, it's a safety critical feature that you don't want to force your vehicles to be reliant on. Will it help? Absolutely. You're at an intersection and you get signaled that somebody's coming flying through and isn't slowing down. That would be amazing, right? The vehicle won't try to move through the intersection when it knows. Most likely, and in almost all situations, we can see all of the dangers, right? And as soon as you make that communication channel safety critical, it increases a huge number of the requirements from the engineering side in terms of how reliable it is. Yeah.
Thank you.
Wonderful. Okay. Thank you very much.